The next thing we're going to talk about are random variables. Well, first let's make a short recap of what we did so far. We introduced probability spaces and we looked at some properties and some axioms, and we looked at some nice tricks and tools that you can use to calculate probabilities of certain events. So we always worked on events so far. And we found some nice rules, but the problem so far is still, how do we define these probability spaces? It's actually quite easy to design a probability space for a certain experiment, for example rolling a die 10 times, but the sets involved, they actually get quite big, and often we're not really interested in the order of the numbers or of the outcomes of these die rolls. But for example, we're interested in how often we actually did get a 6. We're not interested whether it was the first 5 times, but we're interested that it was actually 5 times. And then it gets really hard to explicitly define these probability spaces. And that's when random variables come in very handy. And what is a random variable? Well, we are going to define a random variable simply as a function that takes a set of outcomes and maps it to a real number. So look at this example again. Omega is the set of outcomes if you roll a die 10 times. So it could be a sequence 1, 2, 3, 6, 1, and so on, 10 numbers from 1 to 6. And we map it to a real number, for example 5, because we had 5 times a 6. Now, there's a little remark here. Actually, not every function is allowed. And the reasons for this are hard to explain. The reasons lie in measure theory. And my guess is that if you've never heard of measure theory before, you're not going to be able to write down a function that is not allowed within half an hour. So actually every function, every reasonable function that you can come up with is allowed. And we're also going to use a convention, namely we're usually going to use just the uppercase letter x instead of the full function call x of omega. And the value that the uppercase x variable may take is denoted by the lowercase letter small x. So random variables seem like they overcomplicate things, but actually they simplify things. Let's look at this example for a discrete random variable. We're going to talk about what a discrete random variable actually is in a couple of minutes. But for now, let's assume x, capital X, denotes the probability, the random variable that counts the number of 6s if we roll our die 10 times. And now we want to know whether it's 5, which is the value of this small variable x. And instead of having to make up a probability space for this special question, this is actually just a naming convention for the following event. So this is an event because it's a set of outcomes. An outcome is denoted by small omega. And it's all the events which are mapped to the value small x by the random variable capital X. So what this actually is, it's x to the minus 1, the inverse function of small x. And this is an event. An event if we take simply the most simple algebra you can think of, namely the power set of omega. And the same also works for continuous random variables. Again, we'll define this in a couple of minutes. For continuous random variables, it only makes sense to talk about intervals and bigger sets, not about single values. And the probability that the random variable x maps the outcome, the actual outcome, into the interval AB, which is this shorthand notation here. This is actually, as I said, a shorthand notation again for an event. So that's x to the minus 1 of the interval a, b. And that's again in F. That's a special kind of F. It's the Borel sigma algebra, if you know about measure theory, but it's not so important what this actually is. And you should note the usage of the probability here and of the events. We haven't defined a probability space. We've just used the simple one. And the random variables make our lives much easier because we don't have to care about the event spaces again, but we simply use implicitly the simple one, and we use the random variables as a proxy to these. So all that we need to specify now is the probability measure and the outcomes, but the outcomes are easy. And the way we are going to specify our probability measures, that's going to be the next slides, when we're going to talk about special kinds of random variables. Maybe recall how we defined probability spaces, and there we had a simple example of a probability measure, and this example was that you calculate the probability of a set or an event A as simply the cardinality of A over the cardinality of all outcomes. That was pretty simple, and it worked, for example, for the die. So if the event is that the die outcome is even, you count all outcomes where the outcome is actually even, so that's 2, 4, 6, 3 of them. And you have a total of 6 outcomes, so it's 3 over 6, and you end up with a probability of 1/2. It's simple and nice, but it's way from sufficient for more complicated problems than rolling a die. And to this end, we need to find a standardized way for more complicated distributions, and that's when you need cumulative distribution functions. And because that's such a long word, or 3 very long words, usually people say and write CDF. So if you read CDF somewhere, it means the cumulative distribution function. And a cumulative distribution function, a CDF, is a very special function. And we assume that we are given a function fx. Note the notation here. Fx means, capital F means it's a CDF, and the index x means it corresponds to the random variable x. And it takes a real value, that's essentially the output of the random variable, and it maps it to a value between 0 and 1. And as you may know, probabilities lie between 0 and 1, and that's why we have the following relation. So the output of this CDF corresponds to a very special probability. So namely the probability that the random variable x takes a value that is lower or equal to the small x. For example, in the die roll example, f of x of 3.5 is the probability that the die outcome is lower than 3.5. So that actually means the probability of 1, 2, and 3, because these are the only outcomes that are smaller than 3.5. But of course not every function is allowed, because otherwise we won't get proper probability measures. So what we need to have is that the CDF is between 0 and 1. Well, that's obvious from the definition. But we need also some more probabilities that that is to say, the limits have to be correct. And the first limit is the limit of x to minus infinity. So this corresponds, we could say, the probability that the random variable is lower or equal to minus infinity. And obviously this is the probability of the empty set, because there is no way we can have a value smaller than minus infinity if we have as input the real numbers. And conversely, the limit of x to infinity has to be 1, because this corresponds to p of x smaller or equal than plus infinity, and that's p of omega actually. Why? Because again we have real values, and every real value has to be smaller than plus infinity. And furthermore, we have to have that if we have x and y, and x is smaller or equal to y, then also the CDF of these values has to be smaller or equal. So this means we have a monotonic function. And on the right hand side you can see 3 examples of CDFs, and let's quickly check the properties. The first one has 3 possible outcomes. That's why you have these 3 jumps here, 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 and here. And well, the limits are correct. It's between 0 and 1, and if you go to minus infinity you're at 0, and if you go to plus infinity you're at 1. And it's also monotonic. So values can have the same CDF value, but we have to have some kind of monotonicity. The second CDF that is depicted here shows a probability distribution on infinitely many values, and that's when you have this smooth or continuous CDF, this example here, and it takes values roughly in this interval, because the probability is not increasing when you go beyond these intervals. And these 2 cases, these are discrete and continuous random variables, and they are the most common ones, but you can also of course have mixtures. So you have a mostly continuous distribution in the third plot with one discrete jump in the middle. Now, we have just defined one particular probability, namely the probability that x is smaller or equal than x. Well, how do you create other probabilities? Well, we can look at one very simple example. For example, we want to know the probability that x is in the half-open interval between a and b. And that's the probability of x being smaller or equal than b without the probability of x being smaller or equal than a. Check this for yourselves. That's just rewriting, and maybe you recall one of the rules or axioms that we derived and looked at. This is just the probability of x being smaller or equal than b minus the probability of x being smaller or equal than a. And now we're in the setting that we just defined. That's namely just f of x b minus fx a. And this way you can calculate probabilities pretty easily. There is one little remark that I want to make, which may seem a little absurd if you're not used to it. Well, let's consider again this second CDF here. So the one which is continuous, which has no jumps. And now we want to calculate the probability of the random variable that is corresponding to this CDF being equal to b. And maybe you can think of it yourselves why this is the case, but you can calculate this as f of x minus b minus the limit of x to b of f of x. And because this is continuous, this limit is actually f of x equal to f of x of b, and that's 0. Think about this for a while and digest it a little, but this means that if you have a continuous CDF, then no single point b can have a positive probability because of this particular value. It's called a null set. And now one more thing. If you have two random variables, call them x and y, and they have corresponding CDFs fx and fy. And if these CDFs are equal on every point x, so notice here we have x and y in the indices, but it's the same x here. So if they're equal for all x, then all probabilities for all sets will be the same. And if that happens, we call x and y identically distributed. Identically distributed does not mean that they are the same. It means they can have different outcomes, but they follow the same distribution. There's some small analogy to computer science. You could call the distribution a class, and x and y are two objects of this class. So they share the exact same properties, but they do not behave the same way during runtime. That's what you might say. And that's what you call identically distributed in probability theory. The next thing we're going to look at are certain categories of random variables. And the first category we are interested in are continuous random variables. And continuous random variables are special because their CDF is continuous. That's where the name comes from. And because of that continuity, we can take the derivative of the CDF. And if we take the derivative of the CDF, we get the PDF, the probability density function. And because that's so long, we usually use the acronym PDF, or just for short, density. Now, what does this help us? Well, it makes our lives easier calculating probabilities. Well, there's one downside and one important thing to note. The density does not directly correspond to a probability. In fact, a density can have higher values than 1. It can take pretty much any positive value. But the correspondence to probabilities is as follows. If you consider a small area around a value x, namely the interval from x to x plus delta x, where delta x is a small number, then the probability of the random variable x being in this area is roughly the density value times the width of this interval. So the area under the curve, under the density, that's what corresponds to probabilities. And that's what you can also see in the first picture. You have this density, it's this green line. And if you want to calculate the probability of the random variable that's corresponding to this density to be between 4 and 6, then what you need to do is you need to calculate the area under the curve between 4 and 6, and that's what's marked in red here. And the area under the curve, maybe you remember that from high school or from whatever course you had, is just the integral over this interval. And that's what depicted down here in the properties. if we want to calculate the probability of the random variable x being in the set A or in the event A, then what we do is we calculate the integral over the density within this set A. As a consequence of that, if you integrate over the whole real line from minus infinity to infinity, the result has to be finite, and in fact it has to be 1. Why is that? Because minus infinity to infinity, well, that just corresponds to the probability of omega, and that we know has to be 1. And there's one more property that you need to know, namely that densities are always non-negative. Why is that the case? Well, we know that the derivative of a function corresponds to the slope of this function. And we know that the CDF is monotonic, and it's monotonically increasing. And if something is monotonically increasing, it means that the slope is always non-negative. And that's why the density as the derivative of the CDF has to be non-negative. Apart from the continuous random variables, there is a second category that's very important, and that's discrete random variables. And discrete random variables, they don't have a probability density function, but they have a probability mass function. Why is that? Well, if we have a discrete random variable, that means that this random variable x can only take a countable set of possible values. Countable sets are, for example, natural numbers or whole numbers, integers, or the rational numbers, but not the real numbers. The real numbers are uncountable. And if you think about this for a while, then you will realize that this means that the CDF can impossibly be continuous. And that means we can't do the same trick as we did before with the PDF, that we just take the derivative. That just won't work. But for a countable set, there's a much easier way. You can define a probability mass function. It also maps outcomes from omega to a value between 0 and 1. But this time there is a difference, and this is depicted here. The probability mass function, which is usually denoted as px of x, it corresponds directly to a probability, and it's the probability that the random variable x takes this value x. And notice the difference here. Because we only have a countable set of possible values, a certain value small x can actually have a probability. Notice that we proved that for continuous CDF, p of x being equal to x is always 0, but not for a discrete random variable. And that's why we can use the PMF to represent the probabilities. And it also has some properties that are very similar, namely that the mass is always between 0 and 1. That's clear because we have a probability that is corresponding to this, which has to lie between 0 and 1. And if you take all possible values that the random variable x can take, and if you sum over all of them and take the probabilities, then this has to sum up to 1. So all possible probabilities, they have to sum up to 1, because all these small x's, they have to be distinct. And this is what corresponds to, on the previous slide, the integral from minus infinity to infinity of fx x dx. So notice there is a correspondence between summing over all values and integrating out all values. And the only difference is that one is the discrete case and the other one is the continuous case. And it essentially does the same thing. And also, like in the continuous case, if you want to know the probability of a set A or the random variable x being in this set A, then you just take all values small x, lowercase x from this set A and sum over all of them, the probability mass function. And that's what corresponds to the continuous case, the integral over a f x x dx. And a probability mass function is usually depicted by a histogram, and the height of this histogram corresponds to the probability of the respective value. Random variables turn out to be extremely useful to study the behavior of certain distributions. And the first thing is that given a random variable, we can easily create new random variables. For example, if you have the continuous random variable x, and this random variable corresponds to the temperature in degrees Celsius, and you want to have actually the distribution in degrees Fahrenheit for whatever reason, then you can take the distribution of x and turn it into the distribution of y, where y is then the random variable that corresponds to degrees Fahrenheit. And why? Because the transform between degrees Celsius and degrees Fahrenheit is monotonic. It's actually just linear. And all you need is a strictly monotonic function, s. It can be increasing or decreasing, so it works in this Celsius-Fahrenheit example, it works both ways. Then you can take just the density of x and plug in the transformed value and multiply it by some factor. And this factor is the derivative of the inverse. It's d over dy s to the -1 of y, where s is that transform from Celsius to Fahrenheit. And vice versa, s to the -1 is the opposite, from Fahrenheit to Celsius. And that way you can easily create new random variables. But now let's move on to some more interesting properties of random variables.